Yes, welcome. So today we talk about geometric sequences and geometric series. Unfortunately, I have to turn the music down a bit. So here I give you a geometric sequence. Bn is a times r to the n, r is a positive number. And these arise already as very simple models for populations. So let me show you how this works. If we assume that Bn is the population number at a time unit n, and now the time unit can be days or it can be hours if you look for bacteria, for example, or it can be months or weeks if you look for larger animals. So n is a time unit, Bn is the number of the population at that time, and r is the number of offspring they produce per unit of time. Then the population size on the next day, say, is r times the population size on the previous day. And then we give an initial condition which says how many animals we had at the beginning of the experiment or beginning of the observation. Now we can find a closed formula for this recursion, right? This is a first order recursion, but we can sub it in, so we can write this to be rbn. But now for bn we can use the same recursion, so then this is r times rbn minus 1. And then we can use the same recursion again, and we replace bn minus 1 by r times bn minus 2. So maybe step by step. So this is r squared bn minus 1, then this will be r to the power of 3 bn minus 2, etc., etc. And then this goes to r to the n plus 1 times b0. b0 is the initial condition, so this is r to the n plus 1 times a. So we have already an explicit solution for the bn plus 1 for this simple population model. Now, it doesn't matter if you write it in n plus 1 or in n, so then I can also write this as bn is a times r to the n, and indeed, I have my geometric sequence right here as a population model. Let's look at typical graphs for the population model. So here I show three graphs. One is increasing, one is stable at 1, and one is decreasing. And this has to do with the rate of reproduction r. So if the rate is bigger than 1, if each individual produces more than one offspring per unit of time, then the population grows. And the limit, as n goes to infinity, of r to the n is infinity. So this is the curve for r bigger than 1. If r is equal 1, then r to the n is always equal to 1. So then this is the curve for r is equal to 1. And if r is actually less than 1, this means on average we have less reproduction from day to day. So then we have 0 is less than r less than 1, which is the decaying curve. So geometric series also arise in a more complicated model, which is a model for drug delivery. So let's look at this. So let's say Cn is the drug concentration at day n in a patient in milligram per milliliter of blood. And I assume that 70% of the drug is consumed or washed out during a single day, which means 30% of the drug remains from one day to the next. And 0.2 milligram is added daily to make up for what is lost through the body metabolism. So the question is, write down a mathematical model for the drug concentration in the blood, and what is the asymptotic blood concentration in the body of the patient. So as a model, we use a recursive model. So we write down the blood concentration at the next day, Cn plus 1, is 30% of the previous blood concentration. So we have 0.3 times Cn, but then we add something per day. So then we add 0.2 milligram per day, and very quickly we have our mathematical model. So this here is from previous day, and this is added daily. So it makes a lot of sense. Now let's see how this looks like if we graph this on a computer. So here I show you a view graph. I start with 0 concentration of drug on day 0, but then I have the model which we just derived. And here I show the view graph, and you see it is increasing from 0 after the first delivery, the second delivery, the third delivery, but it does not continue to increase. It kind of settles to a constant level. It settles to a constant level. And of course, the doctor would like to know what is the level. What is the constant level of drug exposure in the body? because this is the target. This is what a doctor would like to know. So we will show you now in this video how to compute this number, how to compute the asymptotic level of the drug in the blood. For this, however, we need to talk a little bit about geometric series. So let's start with a geometric sequence first. And a series is just adding up those terms. So I start with S0, which is the first term, B0, which is just A. S1 is B0 plus B1, which is A plus AR. S2 is B0 plus B1 plus B2. So this is A plus AR plus AR squared, etc. And then this is A plus AR plus etc. plus AR to the n. So the Sn is a sum of the first n elements of the geometric sequence. Now for Sn we can actually find a closed formula how to compute it. So here I write down Sn again. This is a geometric series. Now I multiply this by r. This is a trick. So we multiply by r, then we get AR, AR square, AR cubed, etc., etc. And then the trick is to look at the difference. So I look at Sn minus r Sn. Now see, in Sn we have all these terms, AR, AR square, etc., etc. here, which also appear here, excluding the last term. So if I make the difference of these two terms, I keep the A, which is the first term from here, and I keep this term, which is the last term from this expression, A times r to the n plus 1. All other terms cancel. You can sit down carefully and write it out on a piece of paper. You will see all other terms cancel. So then I factor out 1 minus r on the left, Sn, equals, and here I'll factor out the A, 1 minus r to the n plus 1. And now I assume that r is non-equal to 1. Then we can divide by 1 minus r. And Sn is then A times 1 minus r to the n plus 1 divided by 1 minus r. So we do get an explicit formula for the geometric series Sn. This actually is an important formula, and at some point you need to remember it. Let's look at the geometric sequence. Bn is 2 times 3 to the n, and the geometric series is given right here. So it's 2 plus 6 plus 18 plus 2 times 27, etc., etc. But instead of computing this long sum, I would like to use the formula. So Sn is 2 times 1 minus 3 to the n plus 1 divided by 1 minus 3. So this is exactly the formula I just derived earlier. Now we see in this case that the 3 and 3 to the n, etc., all this is bigger than 1. So the numerator and denominator are both negative. So we can flip them over, and then we have positive terms. So why don't we do that? So then this is 3n plus 1 minus 1 divided by 3 minus 1. So I kind of multiplied minus 1 on the numerator and then the denominator. But then 3 minus 1 is 2, and there's a 2 in front, so they cancel actually. So this is 3 to the n plus 1 minus 1. So it turns out to be a very simple formula. So let's look at the first few terms. So S0, if I sub in n is 0, then I get 3 to the 1 minus 1, which is 2. And this is exactly the 2 from here. If I look at the next term, S1, then I have 3 square minus 1, so 9 minus 1 is 8. Okay, and then if I do 2 plus 6, this is also 8. So the mix is the same thing. And if I look at the next term, maybe S2, then I have 3 to the power of 3, which is 27, minus 1 is 26. And then if I add those terms, I get exactly 26. So this is how the formula works. Now, let's come back to the drug delivery problem. And the drug delivery problem had this form, right? We had Cn plus 1 is 0.3 times Cn plus 0.2. So it has a form of a linear recursion. And here I write down a general form for linear recursion. So Bn plus 1 is R times Bn plus C. So let's compute the elements of this series. So B0 is the initial condition. B1 then is R times B0 plus C, so which is RA plus C. Easy. So B2. This is RB1 plus C, which then replacing B1 with RA plus C, and then multiplying this out, and we get this is R square A. And here we get an RC term and a C term, and I can write this as 1 plus R times C. So the next term, B3, is RB2 plus C. So we sub all this in. Then we get R times R square A plus 1 plus RC. Multiplying this out, we have an R to the power of 3 times A. Okay. And, oh, I forgot my plus C here. I'm sorry. And then we get a term RC, we get an R square C, and we get a C. So putting this all together is 1 plus R square C. If this is too quick, then please take a piece of paper and follow it through on the paper, and you will see that this is correct. So now if we go on and on and on, then we get R to the NA plus 1 plus R square plus etc. plus R to the n minus 1 times C. And now we see a wonderful thing. So this here is a geometric series. Geometric series, right? It is R to the power of n, and we add it up to the number n minus 1. This is great. So we can use the formula for geometric series, which means we get Bn is R to the Na plus, and now we use the geometric series formula with an exponent n minus 1, so then we get 1 minus R to the n divided by 1 minus R, and all this times C. So then this here, I'm sorry I'm a little bit running out of space, but this here is the solution for a linear recursion. We have an explicit solution formula now. And then of course, now we would like to apply this to our drug delivery model from up here. Okay. So here's the drug delivery model again. And so let's write down the solution. So the A term from before, this was a 0, so we start with 0 drug concentration on the first day. So what we really get is then C times 1 minus R to the n divided by 1 minus R. C is 0.2. 1 minus 0.3 to the n divided by 1 minus 0.3. So, and 1 minus 0.3 is 0.7, which we can then put up front. So we got 0.2 divided by 0.7, 1 minus 0.3 to the n. And then this is the same as 2/7 times 1 minus 0.3 to the n. So we get a wonderful formula for the drug concentration, and this is in fact what describes the curve. This is the same curve as I shown before. In the limit as n goes to infinity, then we have the limit as n goes to infinity of 2 divided by 7, 1 minus 0.3 to the n. So we use our limit laws, and this is the same as the limit as n goes to infinity of 2/7 minus 2/7 of limit as n goes to infinity of 0.3 to the n. Now the first term has no n in it, so limit of 2/7 is just 2/7. And the second term has a limit of 0.3 to the n, which goes to 0. So the result is 2/7. So our asymptotic concentration of drug in the blood is 2/7. So let me summarize. A geometric sequence has a form Bn equals A times R to the n. A geometric series is the sum of all those first terms. So A plus AR plus ... plus AR to the n. An explicit formula for Sn we found to be A 1 minus R to the n plus 1 divided by 1 minus R. A linear recursion is a recursion of the form Bn plus 1 is RBn plus C. And we found an explicit solution for linear recursion to be Bn is c times 1 minus r to the n divided by 1 minus r plus r to the n a. Oh, yeah. Hi, Gerlo. Hey, what are you up to? What? You're building a geometric sequence? That's actually funny. Well done.